Good day, everyone. I am Crystalline Fernandez and I warmly welcome you to the General Chemistry 1 class. This section is about organic compounds focusing on bonding patterns in hydrocarbons. So, in this lesson, our objective is to describe the bonding in ethane or ethylene, and ethine or acetylene, and explain the geometry in terms of hybridization and sigma and carbon-carbon bonds. Limitation of the Lewis theory. In our previous lesson, we learned that in Lewis theory, atoms in a molecule form covalent bonds by electron sharing. However, the theory does not describe some aspects in bond formation. Example given, the orbitals which bonding electrons occupy and the strength of the bond. Bond theories. Two quantum mechanical theories give a description about the formation of chemical bonds. First is the valence bond theory, or the VBT, which says bonding electron pairs occupy the atomic orbitals of the individual atoms. Next is the molecular orbital theory, or the MOT, in which, based on the claim that atomic orbitals give rise to molecular orbitals. Focusing on the valence bond theory, bond formation between two atoms involves an overlap between valence orbitals of the atoms. Overlapping orbitals may involve 1. Two half-filled orbitals, or 2. A completely filled orbital and an empty orbital. Bonding in NH3 or ammonia. Consider ammonia. Nitrogen has 3 unpaired valence electrons in the 2p orbitals, while hydrogen has its unpaired electron occupying the 1s orbital. The formation of bonds between nitrogen and oxygen takes place when each 2p orbital overlaps head-on with the 1s orbital of hydrogen. This head-on orbital overlap gives rise to a sigma bond. Since 3 2p orbitals are mutually perpendicular to each other, bond angles are predicted to be 90 degrees. However, experimental value is found to be 106.6 degrees. Moving on, we have orbital hybridization of bonding in methane. Consider carbon, which has 2 half-filled 2p orbitals. In the ground state, it can form bonds with up to 2 hydrogen atoms, forming the carbon or CH2 molecule. Carbon is very reactive as a result of less than 8 electrons around carbon. To attain an octet, carbon must be bonded to 4 atoms like hydrogen. In order to accommodate all the 4 hydrogen atoms, one of the 2s electrons can be promoted to the vacant 2p orbital. At this state, 1s orbital of 3 hydrogens overlap with each of the 3 mutually perpendicular 2p orbitals of carbon, while 1s orbital of the other hydrogen overlaps with the 2s orbital of carbon, suggesting that there exist 2 different carbon-hydrogen bond lengths in the molecule. However, actual geometry of methane shows that carbon-hydrogen bond lengths are equal, and so are all bond angles, which equals to 109.5 degrees, suggesting that the manner by which the 4 hydrogens bond with carbon are the same. This would be possible only if the 4 valence electrons of carbon occupy orbitals of the same energy. In the case of hydrocarbons and organic compounds with oxygen, carbon dioxide and water are produced if combustion takes place with excess oxygen. If oxygen is lacking, carbon monoxide, a poisonous gas, and carbon in the form of black solids called soot may be produced. This illustration shows the shapes of s and p orbitals, as well as the shapes of the resulting sp3 hybrid orbitals. The methane molecule has 4 sigma bonds. Each of these sigma bonds involve an overlap of sp3 orbitals of carbon and 1s orbital of hydrogen. Let us proceed to the orbital hybridization of bonding in ethane. Ethane is a hydrocarbon consisting of 2 carbons and 6 hydrogens with respect to each carbon center. The geometry formed by the surrounding atoms is also tetrahedral. bond angles are close to those observed in methane. With this geometry, both these carbons have sp3 hybridized orbitals involved in the bond formation. Carbon-hydrogen bonds are formed via the sigma overlap between a sp3 hybrid orbital of carbon and one s orbital of hydrogen, whereas carbon-carbon bond is the result of sigma overlap of one sp3 orbital of one carbon and the same orbital of the other carbon. Now we have the orbital hybridization of bonding in ethene. Ethene or ethylene is the simplest organic molecule consisting of a carbon-carbon double bond with the formula C2H4. A double bond implies two bonding pairs shared by two atoms. Upon promotion of a 2s electron into the vacant 2p orbital, the 2s orbital and two 2p orbitals undergo hybridization, giving rise to three sp2 hybrid orbitals. The three sp2 orbitals lie in the same plane and adopt a trigonal planar arrangement. Hence, the geometry of molecules whose center is sp2 hybridized. The p orbital that is perpendicular to the hybrid orbitals forms a different manner of orbital overlap. One sp2 orbital of carbon overlaps head-on with the same hybrid orbital of the other carbon, resulting in the formation of a sigma bond between these atoms. Furthermore, having unpaired electrons, the p orbital of the two carbons, which is perpendicular to the hybrid orbitals, overlap sideways, forming a different type of bond called the pi bond. Together, the sigma bond and the pi bond make up a double bond. A double bond linking two atoms is shorter than the single band connecting the same atoms. However, the strength of a double bond is less than twice that of a single bond since pi bond is weaker than sigma bond as a result of sideways orbital overlap compared to the head-on overlap. Thus, for ethene, the carbon-carbon double bond is formed via sigma overlap of an sp2 orbital of each carbon and pi overlap of the 2p orbital of these atoms. On the other hand, hydrogen bonds with carbon as a result of sigma overlap of sp2 orbital in carbon and the 1s orbital in hydrogen. Having a trigonal planar geometry around each carbon center, bond angles are close to 120 degrees. Following, we have orbital hybridization of bonding in ethine. Ethine or acetylene is the simplest organic molecule consisting of a carbon-carbon triple band with the formula C2H2. Each triple band consists of three bonding pairs. For ethine, hybridization involves a 2s orbital and one of the three 2p orbitals of carbon. The two resulting hybrid orbitals are referred to as sp hybrid orbitals. The two sp orbitals are arranged in a linear manner, thus the geometry of molecules having an sp hybridized center. The two unhybridized p orbitals are mutually perpendicular to the hybrid orbitals. In ethine, one sp orbital of carbon forms a head-on overlap with the same hybrid orbital of the other carbon to form a sigma bond. The perpendicular p orbitals of one carbon can make sideways overlap with those of the other carbon, with the overlap occurring between two parallel orbitals. As a result, two pi bonds are formed. Thus, a triple bond consists of one sigma bond and two pi bonds. A triple bond between a pair of atoms is shorter and stronger than the double bond linking the same atom pair. The other sp orbital of each carbon atom then overlaps with one s orbital of hydrogen atom, resulting in the formation of the carbon-hydrogen bond. Determination of orbital hybridization. To determine the hybridization of orbital in the bonded atoms, first you have to draw the Lewis structure of the molecule. Then, you have to determine the electron group geometry at each central atom. And lastly, identify the hybridization of orbitals in the central atom from the electron group geometry. These steps imply that the observed geometry of a molecule identifies the hybridization of overlapping orbitals. So now let us have our example. For the example number 1, identify the overlapping orbitals involved in the labeled bonds in the given structure of propene below. Now for our solution, the geometry around each carbon center are as follows. As you can see from the geometry, the orbital hybridization in each central atom are as follows. Thus, the orbital overlap in bond 1 is carbon sub sp3 and hydrogen sub 1s, while for the bond 2, the overlap is carbon sp3 and carbon sub sp2. For bond 3, since it is a double bond, then there are two orbitals overlaps involved. These overlaps involve of carbon sub sp2, carbon sub sp2 for the sigma bond and carbon sub 2p, carbon sub 2p for the pi bond. For example number 2, let us determine the number of sigma and pi bonds present in the propene molecule. In our solution, all single bonds are sigma bonds while each double bond consists of the one sigma bond and one pi bond. Thus, propene has 8 sigma bonds and 1 pi bond. To summarize our discussion, let us remember that the valence bond theory considers the bond formation as a result of overlap between two orbitals. Moreover, the theory considers that different orbitals may undergo hybridization. And for carbon, 3 possible hybrid orbitals may form: the sp3, sp2, and sp orbitals. As well as a carbon atom with sp3 hybridized orbitals has a tetrahedral geometry around it, while a carbon atom with sp2 hybridized orbitals has a trigonal planar geometry around it, and a carbon atom with sp hybridized orbitals has a linear geometry around it. Also, let us remember that head-on overlap of two orbitals gives rise to a sigma bond, while sideways overlap create a pi bond. And single bonds are sigma bonds. Double bonds consist of one single sigma bond and pi bond. Triple bonds are made up of one sigma bond and two pi bonds. So these are the references and bibliography of our discussions. You may look this up on the internet or books to further your knowledge and seek more about our topic. Once again, I am Crystalline Fernandez, and I hope that you have enjoyed and learned something from this discussion. Thank you and God bless.